in the previous lecture we have discussed about the deoxidation thermodynamics and kinetics, and in the kinetics we have talked about that is the larger particles are beneficial for flow top of inclusions and optimum gas stirring also helpful, and also we have talked about the liquid product of deoxidation is helpful, and I mentioned that silicomanganese, that is SiMn is a good reductant. SiMn can produce this type of liquid inclusion and then helpful. Okay. So now we will discuss about the Celox probe, that is the probe for measuring the dissolved oxygen. Okay. So that is the chemical, as I said, the total oxygen you can always measure by chemical analysis, which will give you the total oxygen, that is the dissolved oxygen plus the oxygen that remains in the form of inclusion into the liquid still. Okay, that is total oxygen. But if you want to measure only the dissolved oxygen into bath, then you require a certain probe, certain galvanic cell, which is called a Celox probe. So here you can find that you have a solid electrolyte sensor, and here the electrolyte is basically there is the calcium oxide stabilized zirconia, or you can have yttria stabilized thoria. Because what is the advantage or characteristics of the solid electrolyte is that they only allow the oxygen ion to pass through it, right, from the liquid impurity. Liquid has a lot of impurities, but it will only allow the oxygen ion to pass through it. And then, so liquid metal acts as one electrode, and chromium oxide acts as another electrode, right. This is called the reference electrode, chromium oxide, and this is, and the liquid still acts as another electrode, and where we want to calculate the oxygen potential of the liquid still as well as the dissolved oxygen of the liquid still. Okay. So, and we have, you can see in this electrode you have provision for measuring the temperature by thermocouple. Okay, this is the thermocouple that is there, and so it forms a galvanic cell, basically chromium oxide, one electrode, and the dissolved oxygen another electrode. So you can find there is the chromium solid forming the chromium oxide solid. Okay, and then you have the electrolyte is that is the calcium stabilized zirconia. This is the solid electrolyte, and other electrode is the basically dissolved oxygen into the bath, right, dissolved oxygen in the bath. Okay. And then if you apply the Nernst equation, so you can write that when the current will flow, because when the oxygen ion, why it will flow is that when you have a potential difference, that is the potential, the chemical potential of oxygen into the liquid bath and the chemical potential of oxygen into the chromium oxide system. Okay. So if the chemical potential of oxygen into the liquid bath is greater than that of CrCr2O3 system, then only the oxygen will move under the potential gradient of oxygen. So then oxygen ion will move here. So here basically the oxygen ion from there is a dissolved oxygen will form. What are the anodic reaction that will take place is that twice O will basically it will take 2 electrons and forming O2 minus, right, O2 minus. Twice, so now that is okay. That is the simple oxygen atom plus twice E is equal to O2 minus, right, sorry, yeah. So this will be the reaction here, and then you have, then oxygen ion will come here. Here what will happen, that is the O2 minus plus releasing, it will release the oxygen now here, minus that is the minus twice E, you form the oxygen atom like this. Okay. So here this reaction, so here basically you will have an reduction and it is an oxidation and this, and then that is the oxygen ion will move through it, the oxygen ion will move will move through this. Okay, so this way the two reaction that will take place, and this movement of oxygen ion will depend on basically the difference of chemical potential of oxygen into liquid steel and chemical potential of oxygen in the reference electrode. So this difference will drive the oxygen ion through it, okay, or you can say will drive the electron through it basically here. So it will drive the electron basically. Here you can find we are observing two electrons here releasing. So electron will move in this direction. So your electron will move in this direction, that is the electron movement is there, electron will move in this direction and oxygen will move in this direction. So and then so mu O2 still minus mu to reference is equal to minus of ZEF. Z is called the Faraday's constant, E is the EMF generated, and F is the Faraday's constant. Okay. So this is simply the Nernst equation, you know, and here basically the electron flows because of difference in the chemical potential. This is called the concentration cell also. Okay. And the reaction and the chemical potential at the electrodes you can write, there is the oxygen, right. You can see here also you can write this way also, that is the oxygen gas forming the two dissolved oxygen, and the chemical potential is RTLN of PO2, and here RTLN of PO2 is basically the partial pressure of oxygen here, and 4/3 Cr plus O2 forming 2/3 of Cr2A3. So here your mu O2 reference is 2/3 of formation of the standard free energy formation of Cr2O3, because it's 2/3 you can find. So right, you can get these two things. So I know mu O2 still is equal to RTLN of PO2 and minus 2/3 of delta GF G naught F Cr2O3 is equal to minus of ZEF, and then final correlation we can write like this. This is the final correlation, because you can write you can correlate this thing, that is your the equilibrium constant. If you have K naught, you can see equilibrium constant you write, that is the HO square divided by partial pressure of oxygen, or you can write PO2 right, PO2 is equal to your HO square by K naught. So this is your HO square by K naught, and then if you can put there, here we are considering so this is also you can write HO by square root of K naught square, right. So if you put this value here, then it becomes twice RTLN of H by K naught, square root of K naught minus 2/3 of this is equal to 4, because we are exchanging 4 electrons. Basically we are writing the 4 electrons, you can write this way also, that is your twice O plus 4E is equal to twice O2 minus, and then this is the reaction that is taking place here, and the reaction that is taking place here is your twice O2 minus of 4E, and it is forming twice O, write that, twice oxygen or oxygen, then finally the oxygen. So 4 basically the 4 electron basically is getting exchanged, so you can write 4 E and F. So Faraday's number you know, so you can calculate the EMF. So EMF and K is also known to us. So if I know the EMF in the cell, we can simply calculate the HO, that is the activity coefficient with respect to 100% standard state. And if you assume there is the Henry's law is varied up to 100% standard state, HO become W naught. So you can directly get what is the weight percent of oxygen into the liquid bath by using this formula. Okay. So this is the slope Boof, and then now this is the way that is it functions, and now let us consider the deoxidation practice. What are the different deoxidation practice that are in use during the tapping? You can do the deoxidation during tapping of steel from LD to ladle, right. During tapping of steel from LD to ladle, aluminum bars are added. Aluminum bars you can add it and utilize the inertia of the liquid for faster melting of the aluminum. That is one thing people do. Basically, other you require some starting NSA because aluminum has to melt and then dissolve into the liquid bath. So as a result, so you can use the trapping stream, inertia of the trapping stream, and you can melt the aluminum bar and then it can be dissolved and then it will deoxidized. So that's why what happened is that you can keep some aluminum bar just at the bottom of the ladle and then pour the liquid steel. Another effect is that the liquid steel will not directly hit the refractory lining, it will fall on the aluminum bar. That is one way good, and also this inertia help in the aluminum bar. So you can in the ladle you can keep some aluminum bar and tap the steel and you can deoxidize the bar. That is one thing people do, that is the deoxidation into the during tapping. You can do it into the ladle furnace also. When you tap the liquid steel and you can take it to the ladle furnace, and then in the ladle furnace means because it is equipped with the arcing also, such that you can do the arcing, you can compensate the heat and all these things. So because this dissolution process and melting process also involves some amount of heat, so liquid steel may lose heat, so you can compensate the heat into the ladle furnace. It is equipped with the arcing. So you can do it into ladle furnace, and then deep deoxidation at the RH. If you want to do the deep deoxidation, you can do it into the RH with bottom oxygen blowing. So you can do both the decarbonization and deoxidation, and the oxygen bottom blowing will be there. And under vacuum, you can bring down both the oxygen and carbon to a very low level. So deep deoxidation you can do by oxygen, that is called the oxygen bottom blowing. Decarbonization you are doing basically, and oxygen also will be removed in the form of CO, and under vacuum you can bring down both of them to a very low level, because under vacuum the solubility product of carbon and oxygen is also very low. So if carbon is also going down, oxygen will also go down depending on the vacuum level. You can also carry out into the cache OB. There is the composition adjustment by seal argon bubbling. I will talk about that. Here the oxygen bubble stands for, OB stands for the oxygen bubbling. That is you can do the oxygen bubbling. And in case of the cache, you have an envelope at the top such that there is the bubble plume is not exposed to the atmosphere. So you can carry out this operation in a very inert atmosphere, so without atmospheric interaction. And there also you can do the deoxidation and the compositional adjustment. I will talk about the cache OB in a later lecture. So it is used for deoxidation, alloying, chemical heating, starting without any atmospheric interaction. I will talk about that thing. Okay. So now this is the two reference. Now we have come to the conclusion, that is in this two lecture we have discussed basically importance of the secondary steel making as well as deoxidation and its thermodynamics, kinetics and deoxidation practice. So we are making a consolidated conclusion for these two lectures. So the first lecture we have talked about, that is the secondary steel making is an inevitable part of steel making today, because with the that is the first thing. There is a secondary steel making can meet the stringent specification for clean steel and continuous casting. As I say, today we have very stringent impurity tolerance for steel, both from the customer as well as casting practice, like what is called the continuous casting. That we cannot tolerate the impurity to a very low level. We have now demand for steel where the sulfur content should be of the order of 50 ppm, very very low, and then carbon maybe 20 ppm also. That is for the interstitial free steel, what is called the IF steel. We have 20 ppm carbon steel. So this type of steel cannot be made into the primary steel making like LD furnace. As I said, in the LD furnace you can lower the steel to 200 ppm, not more than that, thermodynamically as 1600 degrees centigrade. So if you want to make a 20 ppm 100 times less, then you have to go for secondary steel making under vacuum. So primary steel making cannot meet up this, even the sulfur. So under LD steel making oxidizing process, you cannot remove the sulfur. Whatever you have removed under the blast furnace, that is 0.05, that remains. So if you want to reduce the sulfur from 0.05 to 0.003, that is the 30 ppm steel, or for 0.05, that is 10 times less, then you require some special technique which is called the synthetic slag treatment. You have to make a synthetic basic and reducing slag, and then And also gas stirring is required for very stirring such that your kinetics become faster, and with the synthetic slag and the good stirring you can remove the sulfur to a very low level. As you will find that is, it is not only the synthetic slag but kinetics also very important to make a very ultra low sulfur steel. So those things can be done into the secondary steel making, and that is why that is the, as I said, the primary steel making, the intention is to make it as fast as possible, do not waste time, and make the steel within 40 minutes, and then that crude steel will be treated even from the starting from the deoxidation, and then all other treatment, vacuum treatment, inclusion, injection metallurgy, inclusion treatment, everything will be done, and the gas stirring, that is the homogenization, okay, then deep decarburization, deep deoxidation, deep desulfurization, and then everything will be carried out during the secondary steel making process during the transit of the ladle from the SMS to the caster. So you can save some time also during this process. So during this transit, all the transit time you can utilize for processing, secondary processing of steel. So that way it is saving time and productivity will be high. So this is the aim of the secondary. So nowadays, without secondary steel making, so you cannot produce the steel of today's requirement. So this is the first thing that we have discussed, and the various units, as I said, are there, secondary steel making. And next is the deoxidation. So deoxidation is an important. Now we have talked about in this lecture, that is the deoxidation, and deoxidation is very important because, as I said, there is liquid steel contained around after oxygen steel making, liquid steel contain around 800 to 1000 ppm of dissolved oxygen into the bath. So unless you can remove this oxygen, okay, this will make a problem during solidification, because liquid has this much of solubility, 1000 ppm of oxygen can be accommodated into the liquid steel in the dissolved state, but when you solidify the liquid steel in a solid product, then it do not have that capacity to hold that much of oxygen inside its solid structure. So it has a very, very low solubility for oxygen, solid steel. As a result, during solidification, all this oxygen will come out and it will make a supersaturation in the solid liquid interface, and this oxygen then react with the impurities or carbon, that is all the impurities forming carbon monoxide. If it react with the carbon, from the carbon monoxide, it is a gas, so it forms a bubbles, and if the bubbles doesn't get sufficient time to rise up under the very rapid solidification process called the continuous casting, that is, those bubbles will be entrapped and produces defect. This oxygen, that is the enrichment of the oxygen and the interface, also can react with the other impurities, forming some undesirable oxides, right? So it can form the inclusion oxides. Okay, so those things will happen. So you have to have a deoxidation, otherwise you cannot cast that steel. Second thing is that if you want to make any kind of alloying, then also with this high oxygen level you cannot do any alloying, because all the alloying element that will add, they will oxidize, because the bath is highly oxidizing. So any alloying element you will add, that will oxidize and they make the inclusion, so they will join the slag. Okay, so you cannot, the yield of the alloying will be very, very, very less. So if you want to increase the yield of the alloying, so you have to properly deoxidize the bath. So deoxidation is very important for any future further alloying or the stringent requirement that is required for the continuous casting. Okay, so that is the thing. And then we have studied the thermodynamics of deoxidation, and there we have found that we can lower down the oxygen to a very low level, even with 1 weight% in equilibrium with the 1 weight% of the metal present. Like if you consider the calcium as deoxidant, so when the calcium with 1 weight% calcium in the liquid bath, your oxygen amount can be reduced to 10 to the minus 14 weight%. So very, very low level, almost zero oxygen. And then aluminum, also in case of the aluminum also, so with 1 weight% aluminum, dissolved oxygen in equilibrium with the 1 weight% aluminum can be of the order of 10 to the minus 5 weight%. So very less. Similarly, with 1 weight% silicon into the liquid steel, equilibrium dissolved oxygen will be of the order of 10 to the minus 3 weight%, right? And with manganese, 100% manganese, the equilibrium oxygen will be 0.3. So, if you consider, then the calcium is the most strongest deoxidizer. But the problem is, as I said, calcium is not usually used as a deoxidizer, because for bulk deoxidation it is not used, because it is highly volatile and reactive. So, its recovery is very less into the bath. So, unless you make some injection technique. So, injection technique is important. You cannot dump the calcium on the slag, it will be totally wasted. You have to have some injection technique in place, either submerged lens injection or wear injection. Through wear injection, cold wear injection, you can add the calcium. Okay. Otherwise, you cannot simply dump it. So, but aluminum, silicon and manganese are easy to handle. You can simply dump on the top, or you can use the bar of aluminum for deoxidize the bath. And silicon and manganese are comparatively less stronger deoxidant compared to the aluminum and calcium, right? But still they are used, as I said, they can product silicomanganese together. Silicomanganese as a deoxidizer are very good and used in the plant, because they can form a product of deoxidation which is liquid. And liquid product of deoxidation is very good from the kinetic point of view, because from the removal of the impurities, for removal of impurities point of view, these are very good, because they coalesce and form bigger inclusion and go away from the system, right. So, as we have seen, that is, the inclusion formation is very fast, okay, but inclusion removal, that is the product of inclusion, removal of the inclusion from the system, from the liquid still, is not that fast, is the rate limiting. So, we have to concentrate how to remove this inclusion as fast as possible during this processing time. Otherwise, this oxide product will remain into the liquid still in the form of inclusion that hamper the mechanical properties, right. So, inclusion, that is deoxidation, you are eventually not being able to remove the oxygen from the liquid still. They are remaining in the form of oxide into the bath. So, our aim will be, that is, as fast as possible we can remove this inclusion to the slag. So, for that we have to have a bigger inclusion. Bigger inclusion can be easily removed, because they have more buoyancy, they float up much faster, and we have shown by the Stokes law example. Okay, so they can be moved very faster. So, bigger inclusion, how to form the bigger inclusion? One way is that if you have a liquid product of deoxidation, because the liquid product easily coalesce, form a bigger inclusion and go away from the system. And from that point of view, silicomanganese is very good, because they form a liquid product of deoxidation. So, and another thing is that, as we have said, that is the bath stirring. Bath stirring also helps to carry the inclusion to the slag metal interface, where the inclusion can be absorbed by the slag. Because most of the cases, the final inclusion, this inclusion we are talking about, micrometer inclusion, those will be entrained into the liquid still, and they follow the streamline of the liquid. So, as the liquid, as you know, by gas stirring we can have a recirculating flow pattern. So, this inclusion will be entrained into the moving liquid, and the moving liquid will carry them to the slag metal interface, and then inclusion can be absorbed by the liquid slag. But we have said also, that is, the speed of recirculation also should be optimum. If it is very fast, then the inclusion may be re-entrained into the liquid. They may not sufficient chance to go into the slag. So, there should be an optimum circulation. If the circulation speed is very high, they may be re-entrained into the liquid still and remain forever in the liquid still. If the circulation speed is optimum, then the liquid will help in carrying the inclusion to the slag metal interface, and the inclusion will move away or will be absorbed by the slag layer. So, yeah, optimum stirring is required, not very high stirring rate. Okay. And we have said that is the deoxidation is practiced during the tapping also. Here you can utilize the inertia of the tapping stream such that you take the aluminum bar at the bottom of the ladle and then pour the liquid still over it, and then aluminum will melt and it will dissolve and then it will deoxidized. So you can use the inertia. Another thing is that aluminum, if you keep it at the bottom, that the liquid steel also will not directly hit the refractory wall. That is the one very important. Otherwise, deoxidation can be done into the LF also, because when you, and then there is also temperature compensation unit is also there. There is a arcing system is there in the LF. You can compensate the temperature, because if you add some alloying, you can add the deoxidation. A lot of heat loss take place because of melting. So you can do the deoxidation in the LF itself, or in the cache OV system, where you can do this deoxidation in a more controlled manner under inert atmosphere without any interaction with the atmosphere. So that is you can utilize the alloying element as well as deoxidant more economically. Otherwise, lot of deoxidant can be utilized by interaction with the atmosphere. Okay, so those things are there, and cache OV we will also discussed later on. So another thing is the dissolved oxygen. Another thing is that, as we said, in the plant you will find that is the dissolved oxygen you measure by a particular probe called the Cellex probe, and that is basically a concentration cell, and it uses a solid electrolyte that basically allows the oxygen to pass through the electrolyte only. So you can measure the dissolved oxygen using this probe. Otherwise, you measure the total oxygen by chemical analysis, right? Okay, thank you very much.